All right, we're gonna get started. Welcome, everyone. Welcome to 15150 for the summer 23 semester. So glad y'all could join us. I hope you enjoyed that little sea shanty. It's a traditional Scandinavian folk song. So anyways, as the states, we're here to learn functional programming. My name is Brandon. I'm gonna be your instructor for the semester. Hopefully everyone who should be here should be here. You found the lecture room all right. I left some notes on Piazza, but you're all here, so it should be good anyways. So let's get started here. Before we start, I'm going to have to get started with some administrivia. I have to tell you some logistics, all right? And I know everyone loves logistics, so let's make it quick and snappy. So here's a lesson plan for today. We're going to be talking about a little bit of administrative stuff. I'm going to talk a little bit about the philosophy of this thing called functional programming. I'm going to tell you about some things that are kind of fundamental to doing functional programming called types, expressions, and values. And then we'll kind of talk about how we can actually program in standard ML, the language that we will be using this semester with declarations. Okay. So administrivia, I'm going to talk about myself for a little bit, but hi, my name is Brandon. I graduated last year with a degree in computer science from CMU. I'm an alum. I work as a full-time software engineer for a company called SemGrep doing program analysis, and I do functional programming, which puts me in a pretty cool position where I can tell you that as someone who does this for a living, this is really important stuff. And I cannot stress to you like how lucky I feel to be able to say that, because when I was sitting in your chairs, 4 years ago, I was thinking, okay, this professor who's never programmed anything in his life other than whatever it is that professors do all day, he's telling me, oh, this is important stuff. No, this is actually really, really critical for you, depending on what you want to do. So I'm a full-time software engineer. Raise your hands if you have aspirations of being a software engineer. Okay, that's a lot of you. Some of you aren't proud to say it, but I see it in your eyes. But that's fine, because I can tell you that right now, you got to pay attention, because this is what's up. All right. Okay. And then notes to you: I am not a professor. I don't have a PhD. I'm not a professor. I'm technically a visiting lecturer. You can call me instructor, or you could call me my name, which is Brandon. Which would be preferred, to be honest. But yes, that's the idea of that slide. Here's our course staff. So I TA'd for this class for 3 years when I was an undergrad, and I always loved it when the professors put my name up on the first slide. I did better. I put your faces up there. You're welcome. Those are my TAs right there, 2 of them. Everyone clap for them. So that's me. That's my little mug. I'm also surrounded on both sides by my excellent head TAs, Nancy and Sonia. Nancy's sitting right there. And I also have 6 other TAs: Kaz, Dea, Caroline, Stephen, Brandon, and Michael. You'll note that one of my TAs' names is Brandon. You can call me Brandon. You can also call him Brandon. Just figure it out, all right? Because it will get confusing, I expect, all right? Just don't call me Professor Wu, and don't call me Mr. Wu. That's my father. Actually, my father's Professor Wu too. It's a long term. Anyways, and also give a hand for Dave, who's in the back recording this. Couldn't do it without Dave. All right, thank you. All right, let's move on. So I got to tell you about some course logistics. You're here. You want a grade. Cool. I'm not super inclined towards that, but I got to tell you some things. So you have to be graded. I got to give you homework. In particular, the TAs will give you homework. You'll have a homework every single week. Now, this is a 12-week semester with a week's break in between for what is supposed to be a 14-week course. That means that we have to kind of condense our material by a little bit, but not by a lot, which means that some weeks will be a little bit more stranger than others, because we have to play around holidays. We have to, get through some material that we wouldn't otherwise be able to do if we only had, homeworks due every Tuesday. So the way this works out is that our schedule has 2 homeworks due, or rather, it has 1 homework due that can be on Tuesdays or Thursdays, depending on the week. I posted a handy-dandy little colorful spreadsheet on Piazza that you should take a look at, because that is how you're going to know what is coming up. There's also a nice schedule that's posted on the 150 website, and there's a link to that here as well. Other than that, you're going to turn in your assignments via Gradescope. You're going to receive your assignments via Canvas, and you're going to ask questions on Piazza. You can ask anything. You can ask my favorite color. You can ask my middle name. You can ask my favorite programming paradigm. Spoiler alert for what that might be. If you're not in any of these, please let us know. Let me know. Talk to me after class, because I will not be able to communicate with you. It's going to be a black hole from here on out. Most communication will be on Piazza, so make sure you're checking that. fairly often, fairly regularly. Okay. And then the course website is hyperlinked there. And that has, I will post my slides there. You can see a copy of the course policy, which TAs will go over with you in lab tomorrow. And then there's other handy and different information you might want to see at the website there. Any questions on this? Cool. Okay. So the schedule, I'm going to briefly go over this because your TAs will also talk about this, but it's linked here. It's also on Piazza. It's color-coded by what's going to happen this semester. So the blue slots are going to be lectures. We always have lectures on Tuesdays and Thursdays, with the exception of this one down here because of Independence Day, because the Americans decided they had to be free. And then also we have homeworks due. Homework will be due by these yellow ones, which can occur on a Tuesday and Thursday. I have a laser pointer. And also there's homework coming out on the pink dates. I don't need to go through every single one of these, but just know that this is volatile. Sometimes it's on a Tuesday, sometimes Thursday, sometimes Friday. So make sure you're checking this early and often, okay? And then you also have midterms. Sorry. Okay, and we'll move on. Okay, next thing, your favorite thing I gotta talk about is grading, which my lucky TAs get to do. So the grading policy is gonna be a choose your own adventure, if that's not a dated reference by now. But basically, there are 2 tracks for grading that you get to choose, and I will send out a poll at the end of this week so that you can express your preference. So basically, how this works is that there's a lecture track and a homework track. Now, the lecture track is for students who want to be able to earn free points by showing up to lecture. 3% of your grade will be by just showing up, okay? But that will be taken out of your homework grade, which will otherwise be 42% on this track. On the homework track, it means that you don't want to be graded on your lecture attendance. Maybe you're a night owl and you're only awake from the hours of midnight to 8 a.m. I don't know. If you don't want that, then homework will count for 45% of your total grade, and you will not be graded on lecture attendance at all. Okay, and I will send out a form at the end of the week so that you can determine which one of those you would rather be in. That will be on Piazza after the first week. Okay, any questions on that? To further make it clear to you, I am expressing the percentage of your grade via stripes of Farnham. So percentage of Farnham, this is lecture track. So, most of this is your homework. And you also have this little yellow band here near his chin, which is going to be lecture attendance. All right. And then midterm is 10%, midterm 2 is 15%, and the final is 20%. So these go up in score quite a bit. So midterm 1 will be forgiving, and then the final will be worth a 1/5 of your grade. Okay. It's worth noting that as a class, 150 starts off as kind of like a gradual curve. We're going to start slow because I'm trying to introduce you to stuff you've never seen before. But this will ramp up. Okay, by like week 5, it's going to be a lot more difficult than it was in the first week. So be wary of that and be prepared. If you're cruising through the first week, don't like plan a trip to Lollapalooza or something and then expect to be okay. I mean, you can go to Lollapalooza. I'm not going to stop you. And then finally, here's the homework track. So if you look at the difference, the yellow band near his chin has gone away. That's the only difference. So this will be 45% of your grade as homework. Any questions on this? Great, y'all are superstars. Cool. Okay. But also summer's a time for fun, I think, and this is fun. So I have my handy dandy little Lambda hat here, and which I got from a career event in San Francisco. But this is not just a Lambda hat; it is a sorting hat because you all are being sorted into houses, a la Hogwarts or Harry Potter. Every one of you has been sorted into one of 3 labs that is headed by 2 or 3 TAs, depending. And your lab is able to earn points over the course of the semester by doing certain actions. You can earn points via asking good questions on Piazza, giving good answers on Piazza, and answering questions during lecture. And you can't gamify any of these because I'm the end-all be-all. And if I see you like posting 5 billion questions on Piazza, I'm liable to do worse things and not give you points. So twice a semester, to incentivize you twice a semester on certain dates in the schedule, the house with the largest amount of points will win free boba for their entire class, as well as have an end of year surprise for whoever wins the house cup. So you should, and there'll be candy and stuff too. I don't know. I choose, So keep that in mind. You earn points as individuals, but you also earn points as a house. So it's in your interest to get to know the people in your lab, to get to know your TAs, who will be your mascots through this process, and to get competitive because, free boba, who doesn't love that? And yes, like Harry Potter, I mentioned that. And tomorrow in lab, you're going to choose a name for your house. My first order of business in terms of points is that the house who picks the best name by my criteria will get the first 15 points. So it's a competition already. Think about it. Think about it. You'll have a better idea of what to pick at the end of this lecture. Okay. Any questions on this? I can pretty much do whatever I want. There's no co-instructor. It's just me. So cool. Active learning. Research shows. And now the handy thing about that is if you say research shows as a general life rule, no one will question you. So research shows it's better to learn by exercising your mind actively rather than just passively sitting there and learning. Okay. If you want to do like a lap around the room right now while I'm lecturing, like feel free. Don't actually do that. So to that end, we're going to have still holding this. To that end, we're going to have in-class exercises that are quizzes during class. But before you get all angry on me, you will not be graded on these quizzes. They will not be for a grade. The TAs will evaluate them for points, but they won't be entered into your final grade. The TAs will strictly use it to ascertain like how well you're doing and what they might need to do during the lab tomorrow. Like if you got a bunch of types questions wrong, maybe they'll focus more on that tomorrow. But also the other component of this is that these quizzes are a whole house effort. You can earn points as a house individually by doing the 3 things I said earlier, but every house will take these quizzes together as 20 people. Now, you're not allowed to give each other answers, and we will be listening, so please don't do that. But you can kind of like discuss with each other the methodology and how to solve the problems. And each lecture, the house who wins the quiz will be the victor for that lecture and earn points. So not only can you earn as individuals, you are tested essentially together every single lecture, twice a week. Okay, so it's in your interest to get to know the people in your lab, in your house, and to help them and to make sure everyone's on the same page when you take one of these quizzes. All right. And also it'll be how I gauge lecture attendance as well. So don't skip out on these. And don't there'll probably be like a passcode or something to determine whether or not you're actually in lab. In lecture. Don't give it to your friends. Life's too short. This is a summer class. Come on. All right. Okay. Yeah. So it's a whole house effort to win the house competition, and in particular, the house quizzes every single week. Cool. Wellness. I realize this is stretching on kind of long, but I got to talk about all these things, and also it's important. So wellness. If you didn't have a parental figure who told you this when you were young, I'm telling you this right now. Your health is important. Just letting you know. All right. This means, I heard someone say something, but anyways, the things you're learning are important. Yes, I do think that everything that I'm going to teach you is important, but also what's important is sleeping more than 4 hours a night, eating food, okay? Or otherwise, if you're compromising your health for this class, something is wrong. Talk to me, okay? I'm not here to try and make you not eat, all right? SES admin would not be happy about me for that one. So things that are required. Sleeping is one. Eating is one. For some people, socializing is one. Unless you're a hermit. Raise your hand if you're a hermit. Okay, some people in the back are raising it. It's fine. You get a candy for raising your hand anyways. Too late now. So you have to do these things. So please do it. Okay. Don't compromise on these things just for 150, right? Because that signals something else is wrong, maybe with like planning or your schedule, or maybe some other extraneous factors in your life. I can be flexible when I need to. Okay. I can't do the splits, but like in a different way. Yeah. And also paying taxes is required. Things that are not required are not doing any of these 4 things, especially the last one. If you're not paying your taxes because of me, I'm going to be in trouble. So don't do that, please. Especially the last one. Yeah. The funniest thing is that you can see the footnote at the very beginning of the slide. So you just like spend your whole time like thinking like, what is the footnote going to be about? It's about this. Don't not do it, please. Jeez. Okay. Take care of yourself. If you're having trouble, talk to me, talk to a TA that you trust, either of those things. And if it's something real serious, talk to counseling, talk to CAPS. Okay. You can go to this website. They know what to do more than I do, but also I'm free to help you if it's something within my power. All right. I'm trying to teach you, I'm not trying to ruin your life, contrary to popular belief. So don't let me. All right. So if you're struggling, talk to me. Let's come up with a plan. I want everyone to come out of this class winning. I want everyone to come out of this class passing, hopefully, but also by learning something. Okay. But I got to make sure that you're at the right place. All right. Yeah. Oh, I was going to say something else. Oh, yeah. You might think, oh, yeah, Brandon, you're just saying this because you're paid to say this, and you're correct about that. But also, I'll tell you this, I am paid very, very little to be. I'm a software engineer. I am paid so unbelievably little to be here. If I was doing this just because I had to, I wouldn't do it at all. All right. The fact I'm saying this now means I actually do care about this. So please take care of yourself. All right. This comes up. This is important. Okay. Okay. Does anyone have any further questions on anything administrative, anything that I talked about in the past, 15 minutes? Pity, the first one has a question would have gotten candy. Okay, cool. So let's do this. So I'm here to teach you this thing called functional programming. And raise your hand if you know what that is already. Nice. Okay. It's okay if you don't. A lot of you don't, because this is kind of a level playing ground. We're starting at a place where really nobody knows what's going on. And that's okay, but it's a little different than raise your hand if you took 112. Yeah, so a lot of you learned programming from 112, right? And you probably didn't really know much about programming before. But the way to think about programming, right, is, oh, I'm putting magic script into a box and then it does what I want it to do. I don't really have to tell you much other than that. But when I'm motivating this functional programming thing, when I'm teaching you this functional programming thing, I kind of have to think a little bit more about, okay, like why, right? Like you already know how to put the magic script in a box, but the reason why we're doing this is that there's better ways of doing it. There's better ways of thinking about it. And what I'm going to tell you in this section is kind of why you should care, why functional programming is really, really important for your careers, for becoming better computer scientists, for becoming better programmers. Okay, so let's get on with it. What the hell is functional programming? I probably shouldn't be asking you that question because I'm the instructor, but I'll ask you anyways. What is functional programming? I don't know. Let's figure it out. Okay. Before we can proceed with the details, let's talk about what it is. So, but before I can answer this question for you, I want to ask the question, what is programming? I don't mean like an abstract philosophical sense. I mean, what is programming? I gave you one definition, shoving magic script in a box and making it do what you want. I think we can do better than that. So let's try. So what's programming? It's the act of instructing a computer on how to achieve some kind of operation. You're trying to tell the computer how to do something and you're instructing it. But instructing is the magic word here, because instruction is just a communicative act. I'm your instructor. I'm communicating with you. So what I want you to think about is the act of programming is not a black box. When you write code, you are communicating with the computer. I don't mean in some like hippie abstract, you're communing with the computer kind of sense. I mean, literally, you are communicating with the computer. Okay. And with all communication, there's good communication and there's bad communication. That's why relationship coaches exist, right? Like there are better ways of improving our ability to communicate. And so what I want to teach you is that, whoops. Oh, this isn't working. Oh, geez. Functional programming, we're going to think of it. Our first cut will be that it is an improvement on our ability to communicate as programmers, both to the computer and also to people reading our code, to people who might be us later on reading our code. Okay, because the first step is to figure out what's possible, right? Which is programming. The second step is to figure out how to do it well. I'm here to teach you how to program well. You already know how to program. Let's figure out how to do it better. All right. So before I can answer this question for you of functional programming, let's talk about the goal here. What do I want programming to be? What should it be? Before we can kind of talk about functional programming and how it achieves that. Ideally, good programming should be descriptive. Okay. And whenever I think about this, I think of this old paper written by this pioneer in the field of computer science called Edgar Dijkstra. You might have heard of him. Maybe he came up in 112 or something. Edgar Dijkstra, real smart guy. But he wrote this paper called "Go-to statement considered harmful." This phrase has been memed to death. You see stuff like, for loop considered harmful, global warming considered harmful. But the idea is just that there were these things called go-to statements. Who's familiar with that? Cool. All right. So go-to statements basically mean, this is a C++ code, but don't worry about it. The idea is that we have these things called labels on every single instruction. This is labeled first. And at any point, I can say, in a normal program, we just go line by line. We say, do this, do that, do that, do that. But at any point, a go-to statement can say, drop what you're doing, roll on the ground, and then go to wherever I said to go to. So here, go to first says, stop what you're doing, go here. And then this one says, stop what you're doing, go here. and this one says stop what you're doing, go here. And you could put them anywhere. And old programming used to be full of these things because it's all they knew. This was like the 1970s, whatever. Like we were recently graduating from punch cards, okay? They didn't really know how to program better. And so the phrase spaghetti code, I'm sure all of you know about. This is where it comes from, because look at these arrows that are pointing everywhere. You get like tangled up in a mess where if you tried to trace what you were doing in a program, you'd say, okay, I start here, I do this. Oh, if this is true, then I go here, and then, oh, this is true, so I got to go back, and then, oh, now it's not true, so now I got to go here, and then, oh, now I got to go back. It's a mess. It's a gigantic mess. And the programmers back in the day improved upon this by coming up with things like while loops, like for loops, like conditionals, because we had a more structured way of programming. We wanted to do it, but do it better. That's kind of the mantra for today. Do it, right? But do it better. I'm not sponsored by Nike, I promise. So we want to do things in a better way. So we wanted to make descriptive code that is easy to read, that will clearly communicate what it does. And I'm going to posit to you that that's precisely what functional programming will be able to do for you. Because the first thing you should think about is readable code, especially if you want to like write code for a living, okay? So that's really the most important thing. Okay, but also good programming should be modular. This is a really easy word to throw around, okay? Everything should be modular, but I'm sure you've heard it, but common or distinct logic should be separated. If I'm writing an application to order a pizza, I should probably have different logic for like picking out what I want to put on the pizza, the various toppings, putting the pizza into the oven, delivering the pizza to wherever it needs to go. These are all unrelated things. So I don't want to see a 300-line function where all of these things are mixed and matched together and I can't read it, right? So code should be modular. I'm sure you know that. But another factor that goes into modularity is that you should be able to think about one area of your code without needing to concern yourself with what happens elsewhere. I don't know if you've written code that does this, but I've written code that does this. I was writing a C program for an internship once, and then I made one change on line 5 in file A, and then suddenly I was getting a seg fault on line 300 in file B. What the hell happened? I don't know, because I can't think about everything so densely intertwined, entangled, that I can't think about one area of the code without needing to concern myself with everything that happened everywhere else. That's not modular. That's the opposite. And I don't want that, because how am I supposed to navigate in a code base? How am I supposed to contribute to a project over the course of 5-10 years? I'm really heavily leaning into the software engineering thing because I know it's kind of important to some of you, but like, this is what you should be thinking about. When you're writing code, you're not just writing code for yourself, you're writing code for other people, but also not just other people, you're writing it for future versions of yourself. How many of you have written code and then come back to it in like a week and you're like, who wrote this? Who wrote? Some gremlin took my computer and put it under my name and then hit :W. And it wasn't me, but you did. So that's why code needs to be descriptive. It needs to be modular. It needs to be maintainable. Okay. So maintainability goes hand in hand with both of these things, modularity and what was the other one? Descriptive, right? But programs should be written with future maintainability in mind. When you're writing code, you're not just writing code, right? You're writing code that needs to be iterated on and improved. It's a dynamic process. As a software engineer, what do I do all day? I spend 5% of my day writing code. I spend 95% of my day thinking at my desk. Okay, that's what I do. I think about how to architect my code so that, namely, the person in charge of the project doesn't say, hey, what the hell is this? What's going on? And also so that I can read it later on, right? That's the most important thing. So it's like you're writing code that extends into the future, really, like 1,000 versions of your same code. So functional programming is going to help us in this respect. All right. But yes, if you write it expressively and with future maintainability in mind, that's a-okay. All right. Any questions on these three things that programming should be? Descriptive, modular, maintainable. Quiet bunch, aren't you? You weren't quiet when I was giving out the candy. Just saying. All right. So I want to answer the question for you. What is functional programming? I'm still not gonna. I'm gonna tell you about what's not functional programming, and maybe in like 30 minutes we'll come around to the functional programming thing. So what is not functional programming? Well, let's take a look at an example of code written in Python. And it's okay if you don't know Python because it's just pseudocode. I've got a variable. It's called count. It's 0. I've got a function called increment that accesses it as a global, and it just increments count whenever it's called, and then returns count. Okay. I got a question for you. What does calling the function increment return? Pop quiz. Who's got it? Yeah. Count plus one. Well, what's count? Count isn't bound. Count's free. Give me an answer of a number. That's as good as you can get. Okay. Anyone else want to try? Yeah. All right. You gave me the answer I wanted to hear, so I'm going to give you candy. Great. One. Great. Exactly right. I have another question for you. What does calling the increment function return? All right. You'll get it. Sure. I also saw from you, so I'm going to give you candy too. There we go. Two. And then I got another question for you. What does the increment? No, I'm done with that bit. So the answer is it depends. All right, Stephen was getting to it. It depends. I don't know what increment returns. On the first call, it's going to be 1. On the second call, it's going to be 2. The truth is, it depends. It depends on how many times I called the increment function prior to the latest time. Okay, it'll just be that number. This is what we call state, not like the political boundaries, like a state, like mutability, like what your computer is looking at in the background. It's kind of secret stash. And that's the way you should think about it. What state is your computer has like a sack, and it's like a goblin under a bridge. And like you hand it things and it retreats underneath the bridge, and it like rummages around in its sack, and then eventually it produces you 1. And then you ask for increment again, and then it goes for it, thinks for a little bit, and it reaches into its sack and it pulls out 2. Okay. But like you are not privy all the time to what's in the sack. You don't always get to see what's going on. State basically means that you cannot trust computations because it might depend on everything that's happened before. To understand what this expression, what this function call returns, you have to know everything that's happened in the entire history of the program up until you called it. That's really, really too much. Because by the way, we're human. We have a finite amount of memory, a finite amount of space in our brains. So as our human little software engineers, writing code, I only want to think about stuff I can fit in my little human brain. And if I'm working on a web app that's like been running for like the past 228 hours, I don't have time to read through all the logs. I don't have time to think about all these things. I want to be able to reason about my code in a better way. So this state thing is no bueno, as they say. All right. Suppose you're a chef. Here's an analogy for you. Suppose you're a chef at a 5-star restaurant. Who here likes to cook? You. What's your name? Okay, likes to cook. I'm gonna give you candy. So imagine that you're a chef at a 5-star restaurant run by, okay, and then chef says, dang, I want like a pot of spaghetti right now. All right. Imperative means not functional, basically, for our purposes. All right. If I say imperative, I mean not functional. An imperative program is like a fully stocked kitchen, but there are no rules. There's like a single area in the back in the kitchen with all of the pots and pans and the ingredients, and everyone just goes to the back there to try and get what they can. And there's a bunch of chefs, right? And there's no rules. All the chefs, all the cooks can do whatever they want, and they can mess with each other because if it says I want a pot of spaghetti, so like I say, okay, all right, I get the pot from the back, I get some water, I boil it up, and I leave it there, and then suddenly I realize my creme brulee is gonna boil or whatever it is that creme brulee does. So I go back to it, and I come back to my pot of pasta, and it's full of marinara sauce. Some other cook just decided to take my pot and then put something else in it, and I have no control over that. It depends on discipline. The cooks need to make sure that they don't mess with each other. But if they do, then the kitchen is ruined. A functional program is different because it's like a kitchen where every cook has their own counter, has their own pots and pans, has their own ingredients, their own allspice and sage and saffron and whatever. And they only interact when they've finished something. There's like a little like slot in the wall. And then once you finish your marinara sauce or whatever, you slide it over to the next cook. And that's the only time they ever see each other. They're not very social. Okay. Every cook only interacts when they share stuff that they've finished. That means that a cook cannot possibly mess up another cook's cooking because everyone gets to do their own thing. This is the analogy by which I'm going to talk about functional programs. You might see this as an analogy for also parallelism. Okay, when running programs at the same time, functional programs are safe because they can't mess with each other. Because at the end of the day, they avoid this thing called state. And I'll tell you a little bit about why that is in a second. The imperative program is faster at the risk of salmonella, but I don't really want to go to a restaurant that's renowned for giving me marinara sauce when I wanted like a pot of pasta, right? So by analogy, think about that. We don't want to have salmonella, all right? Is this clear to everyone? At least somewhat. I will periodically drink water. This is one of the things you have to do as well. Keep that in mind. All right. So 2 ways of programming, all right? We've got imperatively, we've got functionally. In an imperative program, computation is by modifying the computer's state. Basically, like you hit the computer in the head a bunch of times and you get to change its mind about whatever it's thinking, and then eventually it spits out an answer to you. All right. And you just have to keep doing that until you get the answer you want. But it's possible that something else might mess with it. Functionally, programming is like, we say that computation is by reduction of expressions to values. And I haven't defined any of those for you yet, but I will in a hot second here. Okay. So in an imperative program, we have something like this. This colon equals is the assignment operator. It's the old school way of doing assignment, basically. So I say x is equal to 2. I change the world. I force the world to be 1 in which x is 2. And then I go and I evaluate x plus x. And I get 4, right? But I have to change the world to do that. In a functional program, this is imperfect, but it'll do for now. We just do 2 plus 2. We see 2 plus 2, and we reduce it to 4. Because 2 is 2 is 2. 2 is 2. And then 2 does not interfere with 2, right? You might not see the difference, but the difference is that when I change the world to one where x plus x is equal to 4, something might go and mess with that. Nothing stops me from changing the world so that I can then do my own thing. And then someone else comes along and they sweep the world out from under my feet and they change it entirely to something else. One more x is 1,000, or x is not a number, or x is, whatever. Stack Overflow happens. Nothing stops that from happening. Nothing stops me from doing that. There's not necessarily a malicious actor. I'm not talking about getting hacked. I'm talking about making mistakes. And making mistakes is also called, by the way, writing bugs, because everyone writes bugs. So the person who's coming here to change the world on you underneath your feet, by the way, oftentimes is yourself. Now, it's almost like functional programming. Really, the thesis here is I'm trying to give you a self-defense course against yourself. Okay, I'm trying to protect you from yourself because you're going to make mistakes. I make mistakes. Everyone does. So let's not make mistakes. Let's not write bugs. So in a functional program, I just have 2 plus 2. I can't change it on myself later. I can't make that mistake. The program prohibits me from doing that. And we'll talk about why that is in the next lecture a little bit. Okay. 2 and 2 are disjoint. 2 and 2 are completely unrelated. 2 is 2 is 2 is 2 is 2. 2 is just 2. Whatever. What's that quote from Everything Everywhere? Just be a rock. I don't know. 2 is 2. Sure. In stateful programs, I said this earlier, but to understand what a stateful program does, you have to know everything that's happened up until that point. You have to know the entire history. That's too much for me. I'm lazy. I want to take the easy way out. Let's take the easy way out. Lazy. That's something you'll learn later. Okay. So that's the analogy. Any questions on this? Yeah. Oops. Nice. What's the? Mm-hmm. Yeah. So I'm not paid to say this, but okay. There are some. Okay. I will say that like functional programming came later as like a refinement of our ability to do programming. Imperative programming was all the world knew at the beginning, right? And there are definitely applications. If you're writing an operating system, if you're working on embedded code, like code that runs on like a microprocessor, okay? You probably want low-level code that runs fast, that runs portably, that doesn't take up a whole lot of memory. So C as a language, for instance, as an imperative language, falls in that category. But the thing is that like you're compromising safety for ability to write C. You're going to make a mistake. You're going to, allocate memory and then forget to free it. And if you haven't taken 122, don't worry about it. But you're going to make a mistake. So there's reasons, okay? I would say writing an operating system is the most feasible one to me. Or if you're writing code that makes a rocket go into space, maybe. But yeah, good question. I'm not paid by Big Functional Beaker, I promise. Yeah, you're good. What's your name? Nice to meet you. Cool. All right. Finally, where are we at? We're 34 minutes in the lecture. Let's talk about it. What's functional programming? What is this thing? So functional programming avoids the modification of state. I don't want to change the world. Don't quote me on that. I don't want to change the world. I don't want to have to change everything around me and then have to be swept from underneath my feet later on. That's such a pain. I'm going to make a mistake. So don't do it. There's no sack. There's no troll hiding under the bridge. And I can't really motivate this to you with a specific example until next lecture. but we'll talk about the main difference on why there is no state in a second. Okay. So here's some definitions for you. So if you were taking notes before or you weren't taking notes before, maybe now you start. Well, that's supposed to be blue actually. One way to read my slides is that generally there will be like a secondary color that goes with the slide, and then anything that's like a vocabulary word or something you're not liable to have seen before, it will be in blue. That's not in blue, but it should be. Okay. So we say that a function is pure, and yes, that is a technical definition. I'm not making that up. A function is pure if it behaves the same as like a mathematical function. In a mathematical function, sine of pi is one of 0 or 1. I don't know which, but it's one of those, and it never changes. It's never different. Sine of pi is sine of pi is sine of pi. I don't have to think about anything. I don't have to think about anything lying in the background, any state when I evaluate sine of pi. A pure function behaves the same. A pure function does not have any what we call side effects. Side effects are basically interacting with an outside world that can change on you. For instance, the real world. So like reading from a file is a side effect. Printing out to the real world is a side effect. But we want to stay inside of our like little mathematical model of programming because things are a lot nicer when you get to stay there. Okay. And a pure function always returns these same outputs given the same inputs. That means that if I have Hagamoro chalk, nice. If I have f of 2, f of 2 is always f of 2. Yeah, you can't really see, sorry. It's fine, it doesn't really matter. If I have f of 2, it's always going to be the same as f of 2, no matter where I am for f of 2. Okay, the function f applied to the value 2, and I'll define those for you in a second. So I don't have to think about any working state behind the board. Okay, everything is as I imagine it. Nothing can change the world underneath me and cause this to be different, because something might do that with the function that returns. I showed you earlier x is equal to 2, and then we did x plus x. If I had a function that returned that, I might assign it at a later time. I might mess with it. So this is always going to be true. So pure functions are going to be the way to go. And we're going to be writing pure functions in 150. We're going to be writing functions that always return the same outputs given the same inputs, which is going to give us really nice properties for reasoning about our code. We'll see. And that's also like a next lecture thing. And let me motivate this to you a little bit more. A lot of problems in computer science are pure. That means that if I give it the same input, I get the same output. Suppose I'm trying to find the shortest path through a graph. That doesn't change on me. Maybe there's multiple of them, but that's not going to change still. If I'm trying to find the nth prime number, well, here's my conjecture to you. Write this down. The nth prime number will probably always be the nth prime number. Okay, that's not going to change. And then the same way, if I'm compressing a file according to some fixed algorithm, okay, if I give it the same file, I'm going to get the same compressed file, same bits and bytes, same everything. Okay, it doesn't matter. So the question then becomes, if I'm solving all these problems that are themselves pure, why should I do it with impure components? Why should I introduce state when this problem didn't need any state, right? I don't need to have any world that's being changed. And I realize I'm talking a little abstractly, but bear with me here, okay? So an important motivation we're dealing with here is we shouldn't introduce state when it's not necessary. When I don't need to be impure, don't do it. It's like, you know that thing where like if you have a gear and you have another gear, they like spin together, like they can spin together basically, right? And if I want to make a bigger gear, like I might string together a bunch of gears and get like extra motion or however that works, right? It's kind of like if you wanted to make a gear and you, instead of putting a bunch of gears together, you put together a bunch of triangles. Like, yeah, you could do it. It wouldn't be a very good gear. But why introduce something that's different as a component to your bigger thing if they chain together nicely? So my analogy to you will be basically, when you're making a gear, make a gear out of gears, okay? That's a little abstract. All right. So I've got 3 theses for you, which probably also you should write down, but they're going to characterize what I'm talking about in this class, and they're going to come up a lot of times. They're going to come up over and over again, okay? And this will be a recurring theme. So the first one, not to keep you in suspense, maybe I will, a little longer. Oh yeah, what's up? Excellent question. We call that an observationally pure function. The thing is, like, behind the scenes, every computer runs on bits and bytes. And by the way, in case you didn't know, every computer exists in the real world. And that means that certain things can happen. There's a whole field of computer science dedicated to like dealing with error correcting codes. Like if radiation comes and flips a bit in your computer. Sorry, I can't stop you from living in the real world, but we can reason about it as if we don't, if that makes sense. Like an observationally pure function, what you're describing, suppose I have some state inside my function. If I don't know from the outside, if I can never know from the outside, it doesn't really matter to me. This is the difference between implementation and abstraction of interfaces. We'll explore this more in 8 weeks. What's your name? Great question. Good question. Okay. Any other questions here to delay the suspense? I might just take a trip to the water fountain. Okay. The first one, recursive problems, recursive solutions. How many of you, a lot of you took 112. There's like a recursion section, right? Like a whole week for it. Yeah. Raise your hand if you really loved that. Oh, we're in trouble. All right. Every function, pretty much every single function you write in 150 is going to be recursive. We are recursion heavy, but it's fine. It's not a bogeyman. It's okay. Recursion is your friend because it turns out a lot of, well, actually I have a whole slide for this, but a lot of problems are nicely solved with recursion. And we're going to see that. A lot of problems are, I'll save it for the slide. Okay. The second one, programmatic thinking is mathematical thinking. Before computer scientists were computer scientists, they were bacteria in the ocean. But after that, they were mathematicians. Okay, computer scientists were mathematicians, and you should know this because you're taking CS at CMU. Our department's full of mathematicians, right? We're a very theoretical school. Math is the language of solving problems. Okay, what do software engineers do? They solve problems. Okay, put some 2 and 2 together. Literally, I guess it's math, right? Math is math is math. Programmatic thinking is just mathematical thinking, and if you do think about things via a mathematical lens, you get so many benefits out of it. And I keep talking about it. There's a whole slide for this. I shouldn't be. Yeah. And the last thesis will be types guide structure. Okay. Have any of you never programmed a language other than Python? Thank God. Okay. Some of you know types. Great. Okay. All of you should know types. Cool. Types guide structure. I'm not going to explain that one. We're going to wait for it. Okay. Copy this down if you haven't already, but we're going to talk about it. So these 3 theses will come up over and over and over again. Almost every function will be recursive. I said that already. But also a lot of computer science problems tend to lend themselves to a recursive formulation. And if you represent a problem recursively, you solve it recursively. It's head and tails, yin and yang. Okay. Lists are recursive. Trees are recursive. All of you know trees. Okay. Other important data structures in computer science are naturally recursive, which means they are natural. You do interesting things on them naturally by recursion. Okay. Recursion is your friend here. So don't be afraid of it. It won't bite you. It's an abstract concept. Also, programmatic thinking is mathematical thinking. So I said the whole spiel about how programmers were mathematicians first. But if you think mathematically, you can use tools from math to help you. And there's a lot of those. So in a functional program, we have, I said expressions. We have stuff like, 2 + 2. This, by the way, in the programming language we're using called SML, this is valid code. Okay. Well, it's part of valid code. It looks like math. It is math. This exists in most programming languages. But the framework by which you view SML programs is that you'll view them as mathematical expressions, and then you can reason about them using mathematical principles. I won't expand on that more for now. But basically, the idea is that if we analyze our code mathematically, we can think about things like time complexity, which I'm sure you're all familiar with, big O, but also parallel time complexity. How fast does my code run when it runs in parallel? Okay. We can also reason about program correctness. Is my code correct? So many times I bet you thought, this code is right. Why am I getting an error? The code is wrong. The compiler is wrong. And it never was. It never once was. And if it was once, I applaud you. That's impressive, actually. But we want to reason about our code's correctness. We want a proof. We want a proof of our program's correctness. And what do mathematicians love? They love proofs, right? So functional programs are really easy to prove correct. And it turns out that when you introduce state, it becomes really, really hard to prove things. Okay. There's a lot of research on this. I'm not just trying to teach you how to write code. I'm trying to teach you how to write correct code. If you're writing just code and it's not correct, what did you write? You wasted your time. Okay, so let's not waste our time. Now that sounds like I'm paid for by big functional. All right, so proofs of correctness. There's a whole, actually, there's a professor who used to be at CMU. I think he's gone now. His whole thing was like logically proving that like code is correct for purposes of like aviation, like airplanes. Because guess what you don't want? Well, guess when you don't want a bug? When you're writing code for like air traffic controllers, determining the paths of airplanes in the sky. Now, I'm not asking you to write code that makes airplanes fly. If you did, I wouldn't step inside the airplane. But if you did, that's a classic joke. It's an engineering joke. Anyways, I'll link it after this class. We're not going to do that. The stakes aren't so high. Okay. But Ileana has this thing he says where he's like, oh, I'm raising you to be the computer scientists that operate, like hospitals. And if you write a bug, you might cause someone to die. And I don't want to be responsible for that. That's a lot of pressure. I'm not going to say that. Okay. I just want you to write correct code. That's it. All right. Just do it. You'll make me happy and yourself happy. Just do it. Still not paid for by Nikki. All right. Types guide structure. You're familiar with types a little bit. I said that programming is this like explanatory communicative process. The process of programming is communication between myself, between future me, between other people working on the same project, and between the computer. Types are the language by which we do this. How many of you have built a booth? Shut up. How many of you, oh, whoops. I should have no notifications on, but that's fine. How many of you are familiar with the concept of booth? Okay, close enough. You build a small structure, right? But like, okay, if I show up to Midway and I have like a plank of wood and I say, all right, boss, I'm ready to go. And I put it down and I nail it down twice. And then someone brings me another piece of wood and they ask, how big does it need to be? And I say, I don't know, big enough to fit next to this thing. Spring Carnival Committee is not going to approve my booth. Okay, it's going to fall down. It's going to kill someone. All right, no pressure. The point is that when I'm writing code, I should architect it in my mind, if not physically on paper, okay? Prior to building the code, but building the structure, I need to plan things. I need a blueprint. I need to be able to scope out everything I'm going to do. That's what types are. Types are a specification. Types are, oh, it's okay, yeah. Functional programming places emphasis on types, which are how you mold out what your program should do. When I know the type of something, I know approximately what it does. Types are a way of kind of seeing into the future. So in addition, when I have functions and stuff, okay, I have a function that takes in a certain type and returns a certain type. That's an API. That's like a library that other people are using. I want to make sure that my APIs, my input outputs are clear to myself and also to people using my code, okay? Because otherwise someone's going to do something wrong. They're going to violate my preconditions and they're going to get unexpected behavior because we didn't agree on what the program should do. I expected an int, he gave me a string. Bad things happen then, okay? So when I'm thinking about my types first, my interfaces are clean and I know how to use my code and other people know how to use my code and I can't use my code wrong. Self-defense, defense against yourself. All right, we're 48 minutes in. Yeah, okay, found time. We're gonna take a 5-minute break. Do whatever you gotta do. Settle in. It's about time. It's no meeting Tuesday at my company. It's worth noting, by the way, when I said I'm a full-time software engineer, I mean I'm still a full-time software engineer. I'm currently still working that job. So I have office hours, but I'll be in my office most of the time doing that. So come by if you're going to come by my office, try to do so during my instructor OH time. It's on the website. Okay. Does anyone have any questions about the whole last part that they will really want to hear before we dive in? Okay, because it was a lot. Yeah. Yes, I will. Yes. I'll give the high tree for that one. Cool. Okay, let's get started. Let's talk about some concrete stuff, please. Finally, okay. Types, expressions, and values are the building blocks of SML. They're the fundamental units you need to know about. Standard ML, the language we're going to be working in. I will also call it SML. That's the shorter way of saying it. So yeah, we'll be using that language in this class. And the mantra you should keep in your head is that in standard ML, computation is evaluation. And I'll tell you about what that means in a second here. So evaluating what? So the idea is that in SML, we have expressions. Expressions are examples of things. We have like 2 plus 3 is an expression. We have 4 times 5. And then also 150 is an expression. These are all examples of expressions. So, and the way that we do things in SML is we're trying to evaluate. We're trying to evaluate them to values. So these may or may not evaluate to a value. So when we evaluate an expression, we take a simple rewriting step. We simplify it by a singular step. We try to simplify it to values. So for instance, 2 plus 3 here is an expression. And I would say that this thing evaluates. What does it evaluate to? Does anyone want to hazard a guess? What does 2 plus 3 evaluate to? Depends on the state. It actually doesn't in this case. So we say evaluates to 5. This is syntax. It's a notation. Keep an eye out. In your 150 templates that we will be handing out, the LaTeX templates, you will have to LaTeX some things in this class. This will be /steps 2. Okay. You don't even know how to make the symbol. We've already aliased it for you. You're welcome. And so this is notation. We're saying that by taking a simple singular rewriting step, we step it to 5. All right. This just got turned around. So values include these things. Values are all, so these are expressions. We also have values. And examples of values are like the integer 2, the string high, and the Boolean true are all examples of values. Okay. What is a value? A value is a final answer. I can't simplify it anymore. What is 2? 2 is 2. Okay. You could go backwards and say 2 is 1 plus 1, but that wouldn't be doing you any good, right? That wouldn't be simplifying it. So all roads converge to the same location. That is a value. All right. So I have that 2 plus 3 will go to the value 5. And at this point, I can't simplify it anymore. I just can't. So therefore, it's a value. Yeah. Oh. What possessed you to ask that question? So standard ML, it does not stand for machine learning. The ML stands for meta language. The reason why was because SML was originally, was that? Facebook. Oh no. What am I going to do with you? SML was originally invented for the purpose of like writing proofs about like math or code. So meta. In SML is very good at things like analyzing programs. Actually, that's what I do for my day job. I write code that thinks about code. So this is a pretty killer app for functional programming. We're going to have a special topics lecture at the end of the semester about program analysis, which is what I do, which is pretty cool. But yes, we have expressions and we have values. And so we apply simplifying rules to things like 2 plus 3 times 4. So the thing is that if I have an expression like 2 plus 3 times 4, I'm going to try and evaluate it. Okay. And we know that taking one singular step is going to simplify it to what? To what's in the parentheses first. I'm going to go left to right here. Okay. If I take one step here, I can simplify this. So I'm going to say this steps to or reduces to is another thing we'll say 5 times 4. But this itself is not yet a value. It's not yet a final answer. Okay. And by analogy, like I'll say if I was asking you for the 4th prime number, okay, it would not be a satisfying answer if you told me the 4th prime number. Or better yet, if you told me the 4th prime number plus 1 minus 1, right? That would be a pretty silly thing to do. So a value is a satisfying answer. It's a final answer. I can't simplify. So 5 times 4 evaluates to 20. Okay. So we took 2 steps to get from 2 plus 3 quantity times 4 to 20. And this is what SML will do. What I'm telling you right now is this is what SML will actually do with your code. It'll try to evaluate it in this manner. We also have some other syntax we're using. This means, I'm trying to use this, but I don't want to confuse you. Like this symbol means a single step, a single simplifying step. And then this one, which is this, and then a asterisk at the top. You can do it via like a caret and then an asterisk in LaTeX. Sorry if this is hard to see. Equals any number. of steps. Usually it'll be until termination, right? So we'll say that like 2 plus 3 quantity times 4. We say that this arrow star steps to 20. After taking an unlimited number of steps, like, or well, 2 steps, but like this is just our shorthand for it, because sometimes we don't have time to write out all of these. I'll just say arrow stars 20. And in particular, if an expression evaluates to a value, so let's say we have an expression E, and this evaluates to value B, then I'm going to give you a shorthand where I say E hook right arrow, this is called B. Okay, so write this one down. This is just all notation. It's notation we're going to be using about because we're going to be thinking mathematically about our code, which means we need mathematical notation to deal with our code. So this is code, and this code E, this expression like 2 plus 2 or 2 plus 3 quantity times 4, evaluates to the value V. Okay, yeah.
Substitute the hook arrow for the arrow with the star, right?
So it would technically be correct to say something like 2 plus 3 quantity times 4. It would technically be correct to say that this is true, but it would not be correct to say this, because that's not a value, right? This is more particular for what you want to say, which is like, oh, this thing goes to a value. We call this a computation trace, and I'm totally going off memory here, not my slides, but yeah, so that's all the things I was supposed to talk about. We call this a computation trace. This thing right here, this is the computation trace of the expression 2 plus 3 quantity times 4. And the goal is that when we compute, when I apply my simplifying rules to this guy, I want to eventually produce a value. But as God would have it, it is not the case that all computation traces produce a value. We're trying, but it doesn't always happen. So in this case it does, but not all expressions do, because we have expressions like 1 div 0. What value does this reduce to? You might guess, based on the fact I just said, not all computation traces evaluate to values. In fact, it does not, right? What happens in standard ML when we evaluate this? Actually, let me show you some code here. So you'll be using a terminal, you'll be using a computer, and on the AFS Andrew machines, you'll write something like SMLNJ to enter the SMLNJ REPL, which is a loop that accepts input, like the Python REPL. On my machine, it's SML, but I think on the Andrew machines, it's SMLNJ, Standard ML of New Jersey. Okay, this is the interactive loop in which you can try out SML expressions and see what happens. Okay, we were talking about 2 plus 2, so I'm going to put a semicolon here to indicate to the REPL that I'm inputting something. And what we're going to get, I'm going to make this a little bigger. And what we're going to get is 4. Don't worry too much about this syntax here. This is just like what the REPL returns to you. The idea is that it's saying, hey, you gave me 2 plus 2. I gave you back 4. That's what it evaluates to. That's the value that it produced. Okay. And if I write something like 1 div 0, let's see what happens. Well, oh my God, I didn't get a value back because it didn't say val. What happened was an exception was raised because, by the way, division is not defined on 0. Okay? It's a partial function. It's not defined there. So what SML's division operator does, which is named div, is that it will just raise an exception on you. There is no value produced. If we go back to the slides, there is no such value. We'll get an exception. There are 3 possible things, and this is a fact. This is a promise to you. Every single SML program, every single SML expression can only do one of 3 things. At the end of the day, it's going to reduce to a value, like 2 plus 3 quantity times 4 reduced to 20, or it's going to raise an exception, like 1 div 0 did, or unfortunately, it's going to loop forever. Sometimes our programs loop forever. Usually, we don't mean for them to. Okay, but unfortunately, that's something that you can do when you have unlimited power to type your magic script into your computer. Yeah.
Just like a little notation. Is the steps to like character going to be the same as like?
Sorry?
Is the steps to character going to be the same as the implication character like?
I believe it's not exactly the same. I usually use like / right arrow personally. It might even be long right arrow. I don't know. But yeah, it's something similar probably. Do you? Kaz, you happen to know? Long right arrow. Yeah, long right arrow. It's longer than the ordinary right arrow. Who would have guessed? Yeah, but you shouldn't have to worry too much about this thing specifically because you should always be able to use steps too. But yeah, okay, good question. Cool. Any other questions on reducing to a value, raising an exception, and looping forever? This is the point where people usually have objections. Oh yes. Values or expressions, yes. We'll cover more of this in lab tomorrow. Okay. I'll also tell you the string concatenation operator is caret. Oh, sorry, what's up?
So if a function raises an exception or loops forever, then is it pure or it's necessarily impure, right?
Yes. You can kind of think of looping forever is in kind of a weird spot where you can think of it as a side effect. But for our intents and purposes, we're going to be working with code that doesn't raise exceptions for now, and we're also going to try and work with code that doesn't loop forever. So just think about the values for now. But yeah, it's kind of a side effect. Yeah. Good question though. That's a really good question. Wow. Okay. So the string concatenation operator is this caret thing. So if I get hi concat there, I get hi there, with no space between. This is not super important to write down. You can try this out at home. Also, I think I'm running low on time. But what does this expression set to? String 1 concat number 50. What do you think? What should this reduce to? 150 times? That's an interesting one. Okay. Any other guesses? Yeah. Yeah, okay, that's one. Okay, yeah. Raises an exception. Okay, all good guesses. Cool. In SML, the thing is, if you're trying to concatenate the string 1 to the number 50, why are you doing that? You probably didn't mean to do that. And if you are meaning to do that, just don't do that. So if this does happen ever though, you probably made a mistake, and mistakes are bugs. Don't do them. But if you do, we want to make sure that we can recover because programmers do make mistakes. So in SML, we're going to decline to try. We're not even going to evaluate the expression. So instead of producing a value like you said, or raising an exception, we're never even going to let the program run. Before anything happens with our future site, we're going to say, hey, you've got nonsense here. What is this? I'm not even going to try with you. It's like a parental figure watching over your toys because you don't get to play with the programming language if you're going to write stuff like this. Some programming languages try to make sense of it. There's JavaScript, for example. If I did something like 1.concat20, I would actually get the string 120. But like, why? I probably didn't mean to do that. And now I'm going to get a mistake somewhere else in my program. This is such a mistake. So SML is statically typed. We're going to try to avoid that by not allowing it to happen. A type is a specification of what a piece of code can do. So I'm going to erase some of this. When I have a type, it's like I have future site. It's like I'm going to know everything that program can do in the future. A piece of code of type int, if it returns anything, must return an int. So we say stuff like notation E:t if E has type T. And we have examples like 1 is of type int, hi is of type string, true is of type bool. Okay, these are all examples of expressions that have types. And I know that if something has a type, then if it produces a value, for instance, an int must produce something, a program of type int must produce an int. A program of type string must produce a string if it produces anything at all, because it might loop forever. I can't prevent that. But what about the runtime behavior of this guy? 1 concat 50. I don't know. I don't know what to do. I don't know whether or not this should return a string or like a list. I think what someone said, what should I return? I don't know. So it doesn't have a type. It's ill-typed. We're not even going to try with you. Okay. And ill-typed programs do not run. So we're going to go through a typing trace. How does SML know the type of an expression? Well, it follows simple rules. So for instance, if I have a typing rule like this, the typing rule for plus is that 2 expressions plus each other only has type int. So E1 has type E1 plus E2 is of type int, only if E1 is of type int and also E2 is of type int. I'm just saying that if I'm adding two ints, I only get an int back. Okay, and that goes both ways, actually. What if I wanted to take the expression like this? 2 plus 3. Hypothesis. It's probably of type int, right? But I've got two subcomponents. I've got this guy plus this guy. So I got to apply my rule. I got to check. Plus only this thing only has type int if these two have type int. So here's the question. Is one of type int? Yes, it does. So that's good, right? It's a value. I can clearly see it has type int, and the SML knows that too. What about 2 plus 3? Is this true? Well, this depends. We're using a typing rule. It only has type int if this has type int and this has type int. And then, so we got to figure out, okay, is it true that 2 has type int? Yes, it is. So we're good. And is it true that 3 has type int? Yes, it's true. Great, we're good. This is a very mechanical process. It's very boring. But this is what SML is doing. The type checker is doing this literally on your code. So what I'm trying to show you is that it's a programmatic dumb process. But these are the rules by which it's figuring out whether or not your code is well typed. And it can always do this. It can always figure out whether or not it has a good a type. And we call that a well-typed expression. So this is a well-typed expression. Okay. Okay. Used if I saw that. Okay. So this is the trace. Okay. What about string 1 caret 50? Well, okay. I'm going to show you something else. There's another typing rule for string concatenation. E1 concat E2 is of type string only if E1 is of type string and also E2 is of type string, right? So our hypothesis is we want to say that, yeah, string 1 caret 50 is of type string. But by our rule, because this thing takes in two inputs, I only know this if I know that string 1 is of type string, which it is, right? Because it's a string. So we're good there. But also if I know that 50, the integer, is of type string. Would anyone like to hazard a guess as to whether or not 50, the number, is of type string? It's not. It's just not. So this is rejected. We say ill-typed. And so this code never runs. The thing is, when I did this analysis on the code, I never had to run the code. I never had to actually try. I don't have to try. I never try because I know that it's going to end up with nonsense because it did not obey the rules of string concatenation. Okay. So that's our trace. Okay. SML is statically typed. I've already emphasized this to you, but ill-typed programs never run. They never, ever run. You can't say something like an ill-typed expression raises an exception, an ill-typed expression loops forever. Those are not true because an ill-typed expression never runs. Okay, the type checker will look at your code, and before it lets you into the playground and lets you run the code, it will say, no, you've got an ill-typed expression. Okay, and this applies to the whole program. No part of the program will run if a single part of it is ill-typed. Okay. All right, this down for emphasis. Ill-typed programs do not run. Everyone say it with me. Ill-typed programs do not run. They do not. If you say something like, this expression is ill-typed, so it raises an exception, I will be sad, and they will be sad. Do not run. Okay, I have a little bit of time to show you real fast some things. I'm going to go back here. So declarations. I showed you a lot of theory. I showed you types. I showed you expressions and values. I didn't show you actually how to program in SML. Like something that's kind of important is you probably want variables, right? You probably want functions. And if you have those things, then you're ready to go. So this is a function. It's comprised of 5 parts. We have the fun keyword here, which is how we know that we're writing a function. We have double, which is the name of the function. We have n, which is the argument that's taking n because it's a function. And also it evaluates to n plus n. And these other two things in here are type annotations. It's saying this is what the type is. So n is of type int. We're saying that the input must be of type int. And then we're saying that the output must be of type int as well. Okay. So these are the different parts to a function. you'll notice that it looks like a mathematical equation, like if I wrote like something like f of x equals sine of x. This is a mathematical definition. So is that, okay? It's just a function. It's just a mathematical function. And this one in particular doubles its input, okay? I'm going to show you some last things. And these slides will be posted, so don't worry about it if you didn't get time to copy it all down. Sorry, I see someone. We apply functions. That means that we use them. In other programming languages, we might write something like double of 2. In SML, we don't have to write the parentheses. We're going to replace this, and then we're going to put a space here. Function application is by what I'll call juxtaposition. I put the function space the argument, or the function space the argument. Okay, we call that function application, and that's just stepping into the definition of our function. So double 2, this thing right here, steps to, well, actually it steps to 2 plus 2, right? If we go back to the definition of double up there, steps to 2 plus 2, right? Because I substitute in 2 for the n, and then that evaluates to 4, right? Fair enough? Okay. I've got some stuff on typing for functions here. I think I'm going to skip it. But basically, some things I'll tell you about it is the function double has type int to int. It's not because of the annotations I put though. Like if I had written this instead, if I had written double takes in n of type int, returns a string, and it's equal to n plus n. Like it doesn't have type int to string, right? Because it returns n plus n. And by our typing rules, we know that if n has type int, this must also be an int. Is that clear to everyone? Right? So it doesn't make sense to say this is type string. The way that this works is that SML will look, like it won't look at your type annotations. It'll figure out the type of everything, and then it'll check, is that consistent with your annotations? In this case, it's going to look at your code, and it'll be like, oh, if I take in n of type int, then I've got n plus n. By my typing rules, that must be of type int. But you said string. You said string, so that's a problem. Ill-typed. Ill-typed program. Never runs. So don't do that. When you write something in your code, it should be true. So it's kind of checking. It's almost like a comment. It's like comment run returns an int, but you say comment returns a string. We're actually checking the documentation for you. So types are documentation, right? Types guide structure. This is a common theme. I'm almost out of time here. So that's basically everything that I just said. And finally, I'm going to tell you that you can declare variables, and you'll do this tomorrow in lab. We use the val keyword, and we say the name of the variable. We do colon, and then we say the type of the variable, and we say what it is. So this would declare a variable called favorite course number, which would be the integer 150. If I said colon string, that would also be ill-typed, and you'd get a complaint. Actually, we can try it out. So like, let's do SML, val favorite course number of type int equals 150, which says it's good, cool. But what if I said that it's of type string? This is a fairly arcane error message, but what it's saying is type error. Bad things happened. You put the wrong type, basically. But we can try again. So if I said n of type int equals n plus n, then I could say, this thing didn't run, by the way. So this declaration still exists. The variable favorite course number in particular still exists. So I'm going to double it. Take it, keep it, or double and give it to the next person. And then I get 300. Yeah, Jesus Christ. Things I have to do to communicate with. Okay, we get 300. We get 300, which is, here's a data reference for you. It's a great movie. But we get 300, all right? So there we go. That's what we get. Cool. So it's like a function declaration, but there are no arguments to type annotate. Okay, simple enough. I will take any questions on this at the end of class, but I have a last thing to say to you because I know we're like pretty much at time. Okay, so we went through a lot. It's okay if you feel like your brain just went through a meat grinder. Okay, that happens to me sometimes. Not the meat grinder part, but I want to emphasize to you that this is important stuff. Okay, what you're learning today, what you'll see in lab tomorrow, is going to shape the rest of the semester. Okay, I talked about what functional programming is. I tried, but I couldn't get to all of it. There's a lot of stuff to say there. Functional programming is a lot of things. It's a paradigm, it's a style, it's a habit, it's an art, but it's also a mindset. Functional programming is not the act of writing down code. It's how you think about your code. So that leads me to this next thing I'm going to say, which is that all programming is functional programming. Doesn't matter what project you're doing, doesn't matter what paradigm, doesn't matter what language you're using. So some of you might say, hey, I'm never going to use standard ML again in my life. And that very well might be true for a lot of you. But it doesn't matter because the ideas you get out of this class are the important ones. It's what you're going to take with you for the rest of your time as programmers, as computer scientists. I love functional programming. I really do. But the things you're going to see in this class are going to be things you've never seen, things you've never done. And it might be tedious. It might be seem unimportant. You're going to succeed and you'll fail and you'll struggle, but you're going to learn. And that's the important part. Because all that I'm asking, all that my TAs are asking of you is your trust. Because we know where this ends and we know where we're going. I love functional programming, but I'm not expecting you to. Okay, I'm not even expecting you to like functional programming. If everything I said today didn't resonate with you, you go out of this like, oh, I have no idea what Brandon was saying. Well, I hope you knew what I was saying, but if you didn't agree with it, that's perfectly fine. That is totally fine. But all I'm asking is that you learn, okay? You see functional language features used in almost every mainstream language nowadays. Rust has an extremely complex type system straight out of PL research. You see TypeScript as a variant of JavaScript being used more and more. You see type checkers for Python being used in production code nowadays. You see algebraic data types in almost every programming language. And if you don't know what that is, that's okay, because you will at the end of this course. A lot of you will never use SML again, but that's okay because these ideas are overreaching, right? Look at where you're sitting. You are at Carnegie Mellon, literally the best institute for computer science in the world. A lot of universities don't even teach functional programming at all. But that's not a bad thing because we're ahead and they're catching up, okay? And that's where we're going here. So I'm gonna, for the last time this lecture, I'm going to say it for a third. I'm going to say it for a final time. I love functional programming, but you don't have to. I'm not asking you to love functional programming. I am asking for the opportunity to change your life. And I do believe that's where we're going. Welcome to 15150. Welcome to the rest of your life. Class dismissed. I'll see you in lecture Thursday. Have a good lab tomorrow.